In this video, we are going to look at how to determine order of a reaction graphically using experimental data. Hey, I'm Teacher Tan. If you like my video, do remember to click on the subscribe button below so that you won't miss any notification as I update my channel.
In the previous video, we have seen how to use initial red method to determine the order of reactions with respect to each of the reagent, and then from there, we can write the red law or red equation. In this video, we are going to look at how to use graph to determine the order of reactions with respect to each of the reagent. For this, we can plot rate versus concentrations graph, and by looking at the pattern of the graph to determine the order of reactions with respect to that particular reagent. Or we can plot concentrations versus time graph, and by looking at the half-life pattern, then we determine the order of reactions with respect to that particular reagent. Or we can use linear graph method to determine the order of a reactions with respect to a particular reagent. For the linear graph method, basically we are going to use the integrated red law equations in linear equations form to plot the linear graph. For a reactions with reagent A be converted to product, the integrated red law equations is concentrations of reagent A equals to negative rate constant multiplied by time plus initial concentrations of reagent A. Actually, there are many ways of writing integrated red law equations for zero order reactions. However, I will suggest you to write it or to remember it in linear equations form so that you know what linear graph you need to plot for zero order reactions. Like for example, if you remember your integrated red law equations for zero order in linear equations like this, then you know that from the linear equations that the concentrations of reagent A, so this is actually the remaining concentrations of reagent A, is the y-axis, and the time is the s-axis, and the negative rate constant is the gradient of the graph, and the initial concentrations of reagent A is the y-intercept. Therefore, we know that for zero order reactions, the linear graph should be concentrations of reagent A versus time, and the y-intercept here is the initial concentrations of reagent A, and the gradient of the graph is equal to the negative rate constant. Now we move on to look at the half-life for zero order reactions. What is half-life? Half-life is time taken for initial concentrations to become half of its initial value. So after half-life, the concentration becomes half of its initial value. By substituting these informations into the integrated red law equation for zero order reactions, we get the half-life for zero order reaction as half-life equal to initial concentrations of reagent A divided by 2 times the rate constant. From the half-life equations for zero order reactions, we can see that for zero order reaction, the half-life is directly proportional to the initial concentrations of reagent. For example, for reagent A with initial concentration as N0, after first half-life, the concentration become half of its initial concentrations value. So means that become half N0 after first half-life. Assume that the first half-life equal to X. For second half-life, the initial concentrations is half N0. So after second half-life, the concentration become quarter N0. And from the graph, we can see that for zero order reaction, the second half-life is half of the first half-life value. So therefore, it is equal to half X. So why? It is because for zero order reaction, the half-life is directly proportional to initial concentration. So as the initial concentrations become half, we will expect the half-life to become half as well. So this is the pattern of the half-life for zero order reaction. Now we move on to look at first order reaction. So for a reaction with reagent A being converted to product, if this is a first order reaction, then the integrated red law equations can be written as log concentrations of reagent A equals to negative rate constant multiplied by the time plus log initial concentrations of reagent A. Again, there are many ways to write the integrated red law equation for first order reactions. But again, I would suggest you to remember it in linear equations form. Because by remembering it in linear equations form, then you know what graph to plot. So from these linear equations, we know that the ln concentrations of reagent A is the y-axis and the time is the s-axis for the linear graph, and negative rate constant is the gradient of the graph, and ln initial concentrations of reagent A is the y-intercept. With this, then we know that to plot the linear graph or to sketch the linear graph for first order reaction, we should sketch or plot ln concentrations of reagent A versus time, and the y-intercept is ln initial concentrations of reagent A, and the gradient of the graph is equal to negative rate constant. Now we move on to look at the half-life of first order reaction. So again, half-life is referring to the time taken for initial concentrations to become half of its initial value. So after half-life, the concentrations of reagent become half of its initial value. Substitute this information into the integrated rate law equation for first order reaction. Then we get for first order reaction the half-life as half-life equal to ln 2 over rate constant K. From the half-life equation for first order reaction, we can see that for first order reaction, the half-life is independent from the initial concentrations of reagent. For first order reaction, assume that the initial concentrations is equal to N0. After first half-life, the concentrations become half N0, and assume the first half-life is equal to X. And then for second half-life, the initial concentration is half N0. After second half-life, the concentration become quarter N0. For first order reaction, we can see that the second half-life have the same value as first half-life. So if first half-life is equal to X, then the second half-life will be equal to X as well. So why? It is because for first order reaction, the half-life is independent from the initial concentrations of the reagent. Therefore, as the initial concentrations become half, the half-life value is still stays the same. That is the characteristic for first order reaction, where the half-life is independent from initial concentrations value. Now we move on to second order reaction. So for reactions with reagent A be converted to product, the integrated rate law equation for second order reaction can be written as 1 over concentrations of reagent A equal to rate constant multiplied by time plus 1 over initial concentrations of reagent A. Again, there are many ways of writing the integrated rate law equation for second order reaction, but I will suggest you to remember it in linear equations form. Again, when you remember it in linear equations form, you know what linear graph to plot. Like, for example, in this linear equations form, then you know that 1 over concentrations of reagent A is the y-axis, and the time is the s-axis, and the rate constant K is the gradient of the graph, and 1 over initial concentrations of reagent A is the y-intercept. Then you know that for second order reaction, the linear graph that you need to plot is 1 over concentrations of reagent A versus time, with the y-intercept as 1 over initial concentrations of reagent A, and the gradient of the graph is equal to the rate constant. So now we move on to look at the half-life for second order reaction. Again, half-life is the time taken for initial concentration to become half of its initial value. So after half-life, the concentrations become half of its initial value. So substitute that into the integrated rate law equation for second order reaction. Then we get for second order reaction, the half-life equal to 1 over initial concentration multiplied by rate constant. From the half-life for the second order reaction, we can see that for second order reaction, the half-life is inversely proportional to the initial concentration. So for example, if we are having the initial concentrations for reagent A as N0, after first half-life, then the concentrations become half N0. Assume the first half-life is equal to X. Then, for second half-life, the initial concentrations will be half N0. After second half-life, then the concentration of reagent A becomes quarter N0. And can you see that for second half-life, it is double the time for the first half-life. So means that it is 2x. So why? So it is because for second order reaction, the half-life is inversely proportional to the initial concentrations of reactant. So if the initial concentrations become half, we will expect the half-life to become double. So for second half-life, the initial concentrations is half compared to the initial concentrations of first half-life. Therefore, we will expect the second half-life to have double the time of the first half-life. So that is the feature for second order reaction. Now I will summarize the Red law, integrated Red law, linear graph, half-life for zero order, first order and second order in this table. So for Red law, for zero order reaction, if the reaction is having reactant A convert to product, then the Red law can be written as red equals to red constant, and the graph of reactions rate versus concentrations of reactant A is a linear graph cutting through the y-axis. And for first order reaction, if it is a first order reaction, then the Red law can be written as rate equals to red constant multiplied by concentrations of reactant A raised to the power of 1, and we will get the directly proportional graph when plotting the reactions rate versus concentrations of reactant A graph. For second order reaction, for Red law, we can write it as red equals to red constant multiplied by concentrations of reactant A raised to the power of 2. And when plotting reactions rate versus concentrations of reactant A graph, we will get a quadratic graph. And for integrated Red law equation for zero order, it is concentrations of reactant A equals to negative red constant multiplied by time plus initial concentrations of reactant A. So remember the integrated Red law equation in linear equations form. Then from the integrated Red law equations, we know that to plot a linear graph, we need to plot concentrations of reactant A versus time. And the gradient of the graph is equal to the negative red constant. For first order reaction, the integrated Red law equation is long concentrations of A equals to negative red constant multiplied by time plus long initial concentrations of reactant A. So again, remember it in linear equations form, and you know that for linear graph, you need to plot long concentrations of reactant A versus time, and the gradient of the graph is equal to the negative red constant. And for second order reaction, the integrated Red law equation is 1 over concentrations of reactant A equal to red constant multiplied by time plus 1 over initial concentrations of reactant A. Again, for the linear graph for second order reaction, you need to plot 1 over concentrations of reactant A versus time, and the gradient of the graph is equal to the red constant. For order reactions, the half-life is equal to initial concentrations divided by 2 times the red constant. From the half-life equations for zero order reactions, we can see that for zero order reaction, the half-life is directly proportional to the initial concentration. Therefore, when plot the concentrations versus time graph for zero order reaction, we will expect the second half-life to be half of first half-life, because the initial concentrations of second half-life is half the initial concentrations of the first half-life. For first order reaction, the half-life is equal to ln 2 over k. For first order reaction, we can see that the half-life is independent from the initial concentrations of reactant. Therefore, we will expect the first half-life and the second half-life for the first order reaction to be the same, even though the second half-life have half the initial concentration if compared to the initial concentrations of first half-life. For second order reaction, the half-life is equal to 1 over initial concentrations multiplied by red constant. From the half-life equations, we can see that for second order reaction, the half-life is inversely proportional to the initial concentrations of reactant. Therefore, we will expect for second order reaction, the second half-life to be double of the first half-life value, because for second half-life, the initial concentration is half of the initial concentrations of first half-life. Now we move on to look at example 1. In example 1, we are being given a set of data for thermal decompositions of dinitrogen pentoxide, and then we are being asked to plot a graph to determine the order of reaction in dinitrogen pentoxide and determine the rate constant, and from the graph determine the concentrations of dinitrogen pentoxide at 2200 seconds. For the first part of the question asks us to plot a graph to determine the order of reaction in dinitrogen pentoxide. So the question mentioned plot a graph and never mentioned is a linear graph. Therefore, we just need to plot concentrations versus time graph, and then by looking at the pattern of the half-life to determine the order of the reaction. So the initial concentrations given is 0.0368 molar. After first half-life, the concentration become half of its initial value, so become 0.0184 molar, and the time taken for the concentrations to become half of its initial value is 1325 seconds, and that is equal to the first half-life. So the first half-life therefore is equal to 1325 seconds. To determine which order is these reactions in dinitrogen pentoxide, we need to determine the second half-life. Now, to determine the second half-life, the initial concentration for the second half-life is 0.0184 molar, and this is half of the initial concentrations of the first half-life. So for 0.0184 molar to become half of its initial value,
It takes 2650 seconds.
and we can see that for the first half-life and the second half-life of this reaction is constant at 1325 seconds. Therefore, we can conclude that this reaction is first order in dinitrogen pentoxide because the half-life is constant. After we get the half-life, then we can determine the rate constant using the half-life equation. For first order reaction, the half-life is equal to ln 2 over k. We write the equation to get rate constant equal to ln 2 over half-life. Substitute the half-life into the equations to give us the rate constant equal to 5.231 times 10 to the power of -4 per second. Sometimes the questions could ask us to determine the remaining concentrations from the graph after a particular time of reaction. Like for example, in this question, the questions ask what is the remaining concentrations of dinitrogen pentoxide at 2200 seconds. So to determine this, we just need to get it from the graph for 2200 seconds. The remaining concentrations of dinitrogen pentoxide is equal to 0.013 molar. Now we move on to look at the next example, example 2. In example 2, we are being asked to use the linear graph method to determine the order of the reaction. So for linear graph method, and given time and also concentrations of reactant V, so what we need to do is we need to plot three graphs. First is concentration of reactant V versus time, and the second one is long concentrations of reactant V versus time, and the third one is 1 over concentrations of reactant V versus time. And which graph gives us a linear graph, then the reaction is that particular order in V. And then from the linear graph, we then can determine the rate constant. As I mentioned before, that for linear graph method, we need to plot three graphs: concentrations of reactant V versus time, long concentrations of reactant V versus time, and also 1 over concentrations of reactant V versus time. Therefore, step number 1, we need to calculate the long concentrations of reactant V and also 1 over concentrations of reactant V based on the concentrations of reactant V data given. We can calculate long concentrations of reactant V and 1 over concentrations of reactant V in a table like this. So the first graph is concentrations versus time graph. Concentrations of reactant versus time graph is to represent zero order. From the data that we have for concentrations of reagent V, we get a curve instead of linear graph. So it means that the reaction is not zero order in V. The second graph that we need to plot is long concentrations of reagent versus time graph. So this graph is to represent first order. Again, based on the data that we calculated, long concentrations versus time graph is a curve, it's not a linear graph. So it means that the reaction is also not first order in V. The third graph that we need to plot is 1 over concentrations versus time graph. This graph is to represent second order reaction. And based on the data 1 over concentrations of reagent V that we calculated, we got a straight line graph. We got a straight line graph for 1 over concentrations of reagent V versus time. Therefore, it means that the reaction is second order in V. After we got the linear graph, which is 1 over concentrations of reagent V versus time, and confirm that the reaction is second order in V, then we can use the linear graph 1 over concentrations of reagent V versus time graph to determine the rate constant. From the integrated rate law equations for second order reaction, we can see that the gradient of the graph is equal to the rate constant. Therefore, to determine the rate constant, we just need to determine the gradient of the graph. And the gradient of the graph is determined to be 0.01253 per molar per second. And therefore, the rate constant for this reaction is 0.01253 per molar per second.